Morning. My name is Doug Rohn from the first A in NASA, the Aeronautics Research Mission Directorate. And I was going to ask you, any of you flown recently, did you see this little display in the seat back in front of you? Well, maybe you didn't. I mean, that's kind of a joke. You didn't see Aeronautics is with you when you fly. But if you, all of us are engineers, we pay attention to the technology on board modern airplanes. And there's been a long line of innovation and overcoming challenges with our partners, NASA's role with the partners. We recently celebrated the 100th anniversary of the NACA NASA continuum when it was the National Advisory Committee on Aeronautics. But my point is that with our partners, NASA Research and Development has overcome numerous challenges, innovations, put things into practice that are with us when we fly today. So I want to talk a little bit about ARMD's, the Aeronautics Research Mission Directorate, some of the innovations, some of the challenges, basically, the challenges that we're working towards. And many of them are, all of them support ultimately the broader NASA strategic plan, where there's pieces in there to talk about revolutionize the current national actually the worldwide, but national transportation system and how all that works. So we in NASA Aeronautics a couple years ago, I'll do it that way, embarked on a kind of a planning, strategic plan development, and I'm going to talk a little bit about some of that internal process thing, just to set the stage to describe some of the challenges. A couple years ago, we embarked on a plan. Charlie Bolden at an AIAA meeting, again a couple years ago, rolled out some of the things we were doing. And basically it's this vision in the 21st century where you take a look at where aviation is going. It's certainly global. There's growth in the Pacific Rim countries. There's growth in the middle class in some of those countries. They want to travel more, just like we in North America travel a lot. It needs to be more sustainable, and the environmental demands as well as just economic demands to make that community stable. And then transformative. We call it tube and wing airplanes for those last 100 years. In the future, that may not be the model, that may not be the technologies that are all brought together. So in that vision of that future of aviation, at least in the 21st century, found that there's basically we talk about these three mega drivers. It's global mobility, environmentally responsible environmental challenges, and then the convergence of technology. And by that I mean we're used to doing computational fluid dynamics. We're used to doing combustion, propulsion, structures, materials, kind of the aeronautics world. Well, there's a convergence going on with other energy devices, communications, networking, things that will change. And I'm going to talk about some of those challenges, what will change the world in the aviation world in the future. So in that process, we came up with these or six strategic thrusts. And again, I'm setting the stage for really where some of the challenges are. And we talk about safe, efficient, global operations. And if you can read that, this enables kind of the full next gen. FAA is implementing the next generation air transportation system and develop technologies that can substantially reduce safety risks as well as substantially expand the aviation system globally. Innovation in commercial supersonic aircraft, and I'll talk about that a little more, but this is basically achieving a low boom standard, which then would enable the community to expand market. Third one, ultra-efficient commercial vehicles. Basically, this is the subsonic ultra-efficient vehicles, and this is pioneering technologies that allow reduced emissions, reduced noise, just more environmentally friendly kind of aviation. Fourth one, transition to low carbon. And I might mention, as I'm reading through these, you might think, well, those are overlapping, Doug. They kind of similar. Well, there are overlappings, but we try to think of these somewhat orthogonally so that we can clearly define what the challenges are. So the transition to low carbon is specifically then looking at drop-in alternative fuels, which again is a convergence kind of thing broadly in the world, as well as other propulsion technologies, whether it's electric propulsion or other technologies that would be lower carbon ultimately. The fifth one, real-time system-wide safety assurance. The National Air Transportation System has been built. It's the safest transportation system. It's been built on knowledge of things that have gone wrong in the past. There's been a huge shift in the recent years towards being a little more forward-looking, looking ahead to what might go wrong, looking at predicting where the system's being stressed and what effect that has on ultimately on safety. But we got to go a little farther than that, because as this system grows, as there's more vehicles, different vehicles, there's things we just don't know yet that we need to be able to assure safety. And then finally, the sixth thrust, we titled it Assured Autonomy for Aviation Transformation. And actually, a lot of this is not unlike, I think, what some of the planetary missions or other needs in NASA have, and that is that the application of autonomy directly impacts what's going to happen, or what's possible, what's the realm of possible. Think about some of the companies that are currently not aviation companies, but maybe in the future, companies like Amazon and Google and UPS and others that are actively looking at delivering a package to your doorstep with an unmanned aerial system, with a drone, dropping it off in your backyard or on your doorstep, or imagine taxis and Uber type vehicles flying down the street here, at maybe 5th story level or maybe 10th story level, flying around DC or around Manhattan. You can imagine, yeah, it's a little scary, but you can imagine autonomy. Autonomy can help there. The analogy for autonomy that I always think of is in Star Wars. Luke had R2-D2 back there, and it was helping him out. So things like that can happen. All right. So again, I'm delving into some process, but I want to set the stage for other things. So we've been looking at this model of this continuous loop. Where here over on the left, those 6 thrusts that I just talked about, we've planned those, and the key word here is the outcomes. And I keep saying I'm going to get to it. I will. The outcomes are what are important. In the top, we've developed roadmaps. These are research roadmaps that enable the outcomes, which are community-based outcomes that we've worked with the community to define where we want to get to. Those roadmaps then guide our internal research planning, as well as identifying where we need innovation to overcome challenges. And then the actual delivery of the results, the performance of what we've done, and our involvement with the partners, because NASA Aeronautics, another thing I like to say is other than the airplanes that we use for research, we don't build anything, we don't operate anything, and we don't regulate anything. So our partners, the manufacturers, the airlines, and the FAA are our customers, and we have to be very, very tight with them in performance, and then in actually defining and feedback, are we doing the right thing? So that feedback then will enable all the benefits that come out of the 6 things that I was talking about. Okay, so we've gone one step farther, and this is a little bit of a advertisement here. If you look at the very bottom of this slide, we rolled out the plan. Actually, Charlie Bolden talked about it a couple years ago at an AIAA meeting, and I forgot to mention on one of my earlier slides on the NASA Aeronautics webpage, a copy of the strategic plan. It's an earlier draft is there. But in a couple weeks at AIAA Aviation 2016 on the 14th, I believe that's the right date, Tuesday morning, here at the DC Hilton is the large AIAA conference, and the entire morning folks from NASA will be going over these 6 roadmaps. But what they're going to talk about are community outcomes. Again, we kind of laid this out, but we've vetted it, we've worked it with the community. Benefits, capabilities are very important. My slide here doesn't say much, but that's really key to the whole story. And then over on the right, research themes. I mean, this is classic. We've got an outcome we want to get to. What's the research theme? And then what are the barriers? What are the challenges? What are the specific technical challenges? What are the broader challenges that we have to overcome? And in my red bubble there in the middle, I just want to say that those barriers are the things that then NASA is tackling. And we've invited, and we have partnership with all those folks I've mentioned, the OEMs, the operators, and the regulators, to work with us on overcoming some of those barriers. But they're not all currently funded. And what I'm going to talk about on the next couple slides has a pretty broad range. As you see, our outcomes span kind of 10-year increments from the next 10 years, 2015, the next 10 years, the next 10 years after that, and then well beyond 2035. Okay, so if you look at the Aeronautics Strategic Implementation Plan on the web, that was a draft from a year ago. We're updating the actual outcomes, but this is a list of all. It's kind of it's a 6x3, but the third thrust actually has a couple different outcomes. But it's in those 3 time frames, the epochs or whatever of outcomes by thrust. These are a little less specific, maybe than what we heard from the other mission directorates, but they still characterize kind of that broad challenge, and they're very challenging things. Many of the things in the left column we're already working on, but they're certainly not solved. We NASA research with our partners, we're working on really all of these boxes in here, but as you move to the right, of course, less and less investment in the really far-term things, but it's not like we're going to wait until those years to actually research them. So let me talk about, I've got a bunch of slides so that you can actually read the words there, and I'm just going to step through those and give you a feel for that. So for the first one, safe, efficient growth in global operations. As I mentioned, the current system is safe. It is efficient. Well, mostly efficient, of course. But NextGen is the focus for the modernization of that system, and what we're trying to do here is to be able to achieve much greater capacity, greater efficiency, and maintaining or even improving safety or any other performance measures. And that's all in the face of growing demand. I talked about worldwide demand, possibility of commercially successful supersonic vehicles in the future, the possibility of thousands of drones. And oh, by the way, we often say UAS, unmanned aerial systems. Well, in the paper you read drones, so a lot of people in NASA have just given up. Drone is kind of a negative word, but hey, whatever floats your boat. I'll call them drones, I'll call them UASs, whatever. But in terms of in that individual domain as well as integration beyond domains, that's what I'm talking about. That's building that broad view across all capabilities. Kind of in the middle range, the 2025, this is beyond what FAA is currently modernizing. This is the full kind of the beyond next gen that talks about gate-to-gate, using an acronym here, TBO, that's trajectory-based operations. Gate-to-gate. Simple example, you know that when you fly, often the aircraft pilot and air traffic control negotiate. They level off and level off and level off in the landing, or the same thing in takeoff. Well, that's less efficient than just shooting straight in. Just a trajectory-based operation is much more efficient. So it's being able to do that, can't be done today globally and broadly, but being able to do that. And finally, out on the right, I mean, this is autonomous trajectory services. This is the ability to do it in a way that's much more efficient. So those are kind of the outcomes that the research that we've talked about would enable, and like I say, we've got partnerships. We've also got Many challenges. If you're in town in a couple weeks, come to the AIAA Aviation 2015 or 2016, and you'll hear even more. So the next one, Strategic Thrust 2. This is one, innovation in commercial supersonic. There's actually an international community. There's a number of companies that are actually interested in. There's a potential for a market here if, from the studies and from what we've heard, if overland supersonic flight was allowed. Currently, the rules are no boom over. I forget what the rules in Europe and U.S. are different. One of them, it's no supersonic flight, and the other one's no boom. But essentially, it's the irritation of the people on the ground when you bang them with a sonic boom. So our initial step is being able to identify, can we build an aircraft, can we design, can we operate it so that there's not that boom, or so that the boom is, and Peter Cohen, who's the project manager, I think he uses the term a thump or a heartbeat or something. A little thump rather than a bang perhaps is acceptable. And so we're doing research on that. And with the international civil aviation authorities, ICAO, standards could be developed then that would then allow overland sonic boom or overland supersonic flight, which then would enable the ability of the community then to further innovate and expand that as a new market. That's kind of the near term. Our look beyond that is once that low boom kind of standard is there, okay, then now it's kind of one at a time. Now we look at, well, what does that mean for emissions? And much of the work that's done in subsonic aircraft propulsion can be applied in supersonic. And then ultimately in the long range, really it's increased the utility. There are people that want to fly faster. You want to fly across the Pacific Ocean and not make it take a long time, and enable the market growth with all those capabilities. Okay, so that was kind of the top level, what we're calling the outcomes for Thrust 2. For Thrust 3, we kind of split it into two pieces because in the commercial world, in the commercial world, there's really two main thrusts right now. The top part here is essentially transport aircraft. The bottom part is vertical lift. Subsonic transport, long haul transports, what Boeing and Airbus and many of the others produce today. That's going to be the backbone of global or even domestic air transportation for years. It's going to be the backbone, but it probably won't last forever. And to be able to sustain the growth of those, we need both in terms of economic as well as quality of life, we need to be able to meet those economic and environmental demands and put us on the path, as I say here in the first time period, on a path to a fleet-level carbon-neutral growth. And that's been an ICAO an agreement to ultimately get to, and I forget all the dates, but carbon-neutral, and then in that middle time frame is to actually achieve fleet-level carbon-neutral growth relative to the time period we started with. And then finally, in the 2030 plus, is actually enable the community to transform their capabilities to have a 50% reduction in the fleet-level carbon output. So there's some. Now you might say, well, Doug, you've been working on aircraft efficiency, CFD for the shape of the aircraft, propulsion. Been working on that for 100 years. Well, we have, but getting to these levels is really a tough problem. So there's plenty of challenges there. Can high bypass ratio turbine engines, jet turbine engines, do it? Of course, but there's significant advancements needed in many of the pieces parts. If I look down on the bottom here, we're talking about vertical lift, and although vertical lift perhaps isn't as big of a market, it's a significant market because of the kind of the vision, if you will, of where the future of civil aviation. I talked about thousands of little vehicles or even man-rated vehicles flying around the concrete canyons in a central city. Well, travelers want that flexibility. People, we all want that flexibility to be able to go where we want to go, when we want to go, get there fast, make it cheap. So there's, in terms of moving people, moving goods, or providing a service, the vertical lift community is a very important piece in that broader puzzle. So some of their challenges, increasing the capability, both in terms of economics, efficiency, and noise really are the buzzwords there again. Economics of overall efficiency and noise. So in the kind of the near term, it's all about reducing operating costs through that increased capability. In the middle one, it's expanding the markets. If we can introduce new configurations, it will expand the markets to give us that additional mobility. And then finally, in the out years, it's just broader, fuller spectrum of vertical lift vehicles that provide all the services that you can imagine. So, large number of needs, pretty significant investment by NASA research in this what we call Thrust 3. Thrust 4, again, remember they're not overlapping, they're not totally orthogonal, but trying to focus on what's the challenge. This one is specifically about lower carbon. And there's two pieces to this. There's alternate fuels. Petroleum-based fuels are hugely important, hugely efficient, a lot of energy, but there are other fuels other than the petroleum-based ones that could be lower carbon. So that's one approach. And then the other approach is alternative propulsion methods. Could be electric propulsion. That's probably the primary one, but hybrid electric, all electric, alternative methods there. And again, the vision, if you think about the vision for the future, it has a lot to do with new vehicles, new needs and expansion of current needs, more and more aircraft. The driver is to have that low carbon. So in the first 10 years, it was just introduction of those things. In the next 10 years, it's actual alternative propulsion systems, whether they're alternate fuel-based or alternate propulsions themselves. Actual introduction in the 2025 to 2035 range. And then in smaller vehicles. And then in the 2035, 20 years and more beyond, introduction of those alternate systems into aircraft of all sizes. And by all sizes, I literally mean transport aircraft. In the middle range, we'll probably have the ability to do that in the smaller vehicles in that time frame. Okay, the Thrust 5 is probably the hardest one to explain, but it's also one of the ones that is really pretty exciting when you think about it. We talk about real-time system-wide safety assurance as if it's new. Well, in a way it's new, but yet it's also going on right now. As I mentioned before, the system is safe, but if we expand the awareness, expand the system's awareness of all these new aircraft that I've already been talking about, new operations, new operators, expand the awareness so that in real time we can monitor and alert in all of those new operations that come up. In the next time frame, the challenge here is really to be able to integrate that prediction back into all of the applications that we have running now, and then in the out time frame, it's make that adaptive, make that adapt to whatever comes our way, if you will, in the future, and then provide through human automation teaming, provide a real-time safety threat management, provide the feedback, provide the warning, provide the recommendations for changes so that things can be done. And in this one, I forgot to mention in the beginning, I am talking about the whole when I say the system, I really mean the system, and that's the pilot, the aircraft, the operating companies, dispatchers, the air traffic control, what's going on the ground, what's actually going on the airplane. We talk about the Internet of Things. Well, the Internet of Things, aircraft, engines, pilots, systems on board is really pretty exciting. That think about what could be done. And then the final one is autonomy, and here kind of the vision, as I said earlier, people want to fly anytime, anywhere, on their schedule in a fraction of the time. There could be 1,000 more vehicles, little tiny vehicles, on up to the full-size aircraft flying at one time, and all of that with keeping safety in mind and not harming the environment. So again, there's a radical kind of opportunity to expand our ability to do that by emphasizing or tapping into the power of autonomy. So in the nearer term kind of challenge, and I think the ones that were on your sheet were actually all this first column, the nearer term, the 2015 to 2025 timeframes. It's the introduction of more aviation systems, and I haven't been very specific here, but capable of carrying out kind of functional level goals more than we have today. The next range is expanding that level of trust. The National Academies did a study for us a couple years ago on this subject, assured autonomy, and one of the big challenges is how do you build that level of trust? How do you earn that level of trust with the system that's that we're willing to put ourselves in the seat on as a passenger? And then also, how do we have it be able to learn in kind of the out years? It's distributed, have the system learn, and be able to carry out higher level goals rather than the more specific functions. So that one, there's actually a lot of cross. We haven't worked it heavy yet, but there's a lot of cross with the rest of NASA, with the rest of the agency in terms of automation, and our actual researchers are involved in multiple mission directorates. Okay, I've got just a couple minutes. I want to give one quick example. Actually, it's several examples, but an internal process that we've mentioned. Kira mentioned before asking the right questions. So internally, we've done an approach for early stage innovation, just an example of a process, asking the right questions, and kind of what do we get. So if you ask the right question, what are the big questions? What is the system level issue? Can we safely and unobtrusively integrate UASs into the environment? Can we do that? Okay, so think beyond the current. We've asked our people then to come up with convergent solutions, the second box. Convergent means integrate the non-aeronautics traditional work, whether it's power or networking or computation, things that we haven't done before. Converge those, show the feasibility. Am I violating the second law of thermodynamics or not? And then ultimately the knowledge that's gained then can be used to feed back and to overcome those barriers and produce the outcomes ultimately they want. So this is, my last two slides are just a snippet of a few things that have been worked on. They're certainly not comprehensive. And the other thing I haven't showed you is what the other 640-some million investment in NASA Aeronautics research, what we're actually doing. This is only a small fraction of that. So I ask a question, can I create a maximum efficiency, top row there, maximum efficiency system? Well, here's an idea. Converge electrochemistry and nanostructural technology. Build the structure and the battery together. There's value there in maximizing efficiency. The second row, can a UAV fly as safely as a first-class system, i.e. how we fly vehicles in the NAS, in the National Airspace System today? Well, that pyramid over there, pilot in the box. If the system operates as a pilot, even though it's autonomous, you think of it as a pilot. Create an operating system that's certifiable. We've spun in some actual space technology, NASA space technology. And the one on the bottom is, can I merge a revolutionary concept with other challenges? And the concept is a digital composite fabrication. The picture's kind of hard to see, but it's thousands of identical parts, just like there's thousands of transistors on a chip. Thousands of identical parts, put them together and build an adaptive wing that can perform functions that we need. Again, it's just digital composite fabrication. And the last couple that I just want to show are Can we create, top row there, this is low carbon. Can we create an aviation system, again, with maximum efficiency? Well, alternate paths, overcoming challenges, high voltage DC versus high voltage AC. There's materials and controls problems. You know, can the controls handle it? Is the installation sufficient? All those kinds of things. Another example of solving a problem. The middle one, I don't know if that, it does work. Okay, learn to fly. Granted, a bird is, you know, built when it hatches from the egg. It's got wings and feathers. The feathers grow. It's got wings, and you know it's going to fly. Well, we don't know for sure. That particular bird has to try it, has to play it. So play with it. So the idea with us is that we'd take the current paradigm, which you can't quite see there in blue, which is ground-based testing, wind tunnels, build the structural model, build the control laws, test the heck out of it, with a new paradigm that's learning, like the bird. The bird already has wings and feathers, but the bird learns how to use them. And in real time, also, we would do the real-time modeling. The bird learns in real time. So it's rapid flight testing with learning technologies to make things faster and cheaper. And then the last one is accelerating certification of future configurations. And the little picture there is what we call a truss brace wing, one of our partners' concepts. Because of the certification process is so important, uncertainties tend to accumulate and make it over-designed, if you will, so that the idea here, and digital twin is something that's grown in the community. The idea is to have a digital twin that operates digitally, just like the actual aircraft operates, and that allows us essentially to lower the uncertainty bands, both for future aircraft as well as that one. So those were just real fast, a few examples. I'll take any questions from you.
So I have a question when it comes to assured autonomy, just in general. NASA's approach to the concept of assured autonomy. We certainly seem to be quite comfortable with the fact that we have a human flying an airplane. Clearly, most of us got around today by that mechanism. We don't have assurance that that pilot is not going to make a mistake. So why is it that we hold our technology to that ideal, and we've dropped the notion of risk out of the equation when we are pushing our technologies? How do we balance that equation? Because if we push too hard toward absolute assurance, we can't get to those next technologies.
Right. Okay, so I'll answer that with essentially asking the same question. I agree with you. The bottom line is the balance. It's doing that, ensuring that the balance is there. There are many technologies today that are autonomous. The system, collision avoidance on commercial aircraft gives its total, as a system, it's totally autonomous, and it tells the pilot, you know, pull up, or dive, whatever it actually says. And then the pilot takes that action. But that system, everybody trusts because it works. So that's why I say I'm answering your question kind of with the same question, is we do have to develop that assurance. We recognize that the way today is, the pilots, the controllers, all the human elements, sure, they have their weaknesses, but they also sometimes save the day, if you will. I mean, they're able to think and adapt. So we're trying to do that balance, and as I mentioned, one of the key things out of the National Academy's report was how do we, again, I'm asking the same question, how do we get public trust? How do we ensure that there's trust in that new system?
I'm going to try to augment that, sorry.
Sure, sure thing.
You made me think, I'm wondering if, can the human better identify that they made the mistake? I'm sure autonomy, you can do fault diagnosis, fault detection, isolation recovery, but when that fault is that system that's supposed to make that, can they recognize it and adjust for that, where the human can in most cases? And the other one is the human learns to fly over their experience. Are we there yet on the autonomous side? But fantastic question.
In your last 2-3 slides, you mentioned some of the examples, and then it says selected for FY16. So I was just wondering, what does that mean? Is it selected through a BAA process, or is it selected through?
Okay. Those examples were all internal. I was given an example of a process of starting with a question, and let's see if we can come up with a solution, and let's check it out. We did that internal. It was kind of like a BAA process, but internal with the folks. And each of those activities are, I don't know, a couple $1 million, half a dozen people working. Some with partners. Some actually have external, either universities, small businesses. Trying to think if any of those actually have the big businesses. They may. I just don't remember. Okay. Okay, again, thank you. Thank you very much.